Okay, so today we talk about discretization techniques and algorithms. So typically, if we need to work with manifolds and geometric entities, we would like, if we have to work with them in a computational way, we would like to reduce them to finite pieces of information, usually to combinatorial structures like graphs or multigraphs. And or in general, discrete finite structures that can be fed to algorithms or whatever we need. So what we usually do is that we are examining a quantity, quality, piece of information on our manifold, geometric object on our manifold, and we find a way to approximate it with a sequence of finite structures that, in some sense, converge to what we want to study. That's what we already. So an example of this is the theorems about the convergence of the graph Laplacian to the manifold Laplace-Beltrami operator, where we didn't really have the graph Laplacian, but well, anyway. Obviously, I mean, there is no unique way of doing this. There is no unique structure that is good for everything. So mainly, I will be giving examples of things that don't work in the next 10 minutes or so. So the first example comes from Calculus 2. Multivariate calculus. When you want to compute the area of a surface, you, well, usually you remember the length of a curve, which, if the curve is nice, I mean, let's say it's C infinity, whatever, is usually obtained by constructing a polygonal approximation of the curve. So we approximate the curve with a piecewise linear function, and then we set the length of the line segments epsilon going to 0, and the usual result is that the length of gamma is the supremum of the sums of the length of all the segments. I mean, it's very imprecise written like this, but the main idea is that the polygonal curves tend to the curve in a nice enough way so that the length of the polygonal curve tends to the length of the curve. And as the straight lines are geodesics in the plane, the length of the polygonal will be always less than or equal to the length of the curve. So it's a supremum. Now, with a surface, you could try and do the same. So let's consider approximating a surface by taking triangles on the surface. We take points, we build up triangles, and we let the number of triangles go to infinity. So we consider a cylinder with radius r and height h, and we built on it triangles this way. So let's see. We divide the circumference in, well, here is only half, but you also have the other half. I didn't draw it. You take the circumference and divide it into 2n pieces, the half circumference in 2n pieces. And then you divide the height of the cylinder in m pieces. So these are 2n and these are m. And then you build triangles like this. At every step in height, you redraw the circle, like this green one. You divide it also in half of it in 2n parts, and you build triangles by just going up and down from one circle to the other. So you take only the, I don't know, even points here, the odd points here, and you build the triangles like this. So usually the base of the triangles keeps 1 point, which gives on the other circle the third vertex of the triangle. So it's easy to compute the area of these triangles. And we would like to say that when the parameters, so m and n, tend to infinity, the area of the triangulation tends to the area of the cylinder. However, this is the area, the sum of the, okay. Here we need a sum here somewhere, or just, no, not really a sum, but well, technically a sum, yes. But then they all have the same area, so it will be just this function times the number of triangles. So this is the area of one triangle. I mean, you can compute it, it's not that difficult. This is the base, and this is the height. And there is a half, well, this is half of the base, and this is the height. And you should multiply this for the number of triangles, which is n times m, 2n times m, 4m times n, something like that. And then take the supremum over m and n. Unfortunately, this supremum is plus infinity. So it depends on how you select m and n. If m equals n and they tend to infinity, then the area tends to 2 pi r h, which is the correct answer. But if, for example, m equals n cube and they tend to infinity, the area diverges to plus infinity. So this triangulation is not, I mean, some triangulations work, some other don't work. So it's not enough to say we divide it into triangles and let the number of triangles tend to infinity. It doesn't work. It doesn't work here, it doesn't work in Rn. So this is why, nope. No, I didn't write it. Okay, anyway, this is why the area is usually computed in the parameterization space, in the parameter space. So when you want to compute an area of a surface, you parameterize it, and then you write an integral over the parameter space. Now, another example, curvature. I won't be giving the full example here, just a note. There are works from end of the 90s and beginning of the 2000s, one by Chigger and one by Petrunin, that show that in dimension greater or equal than 3, if you approximate a a manifold by, it won't be a triangulation anymore technically. Well, I mean, it's still called triangulation, but it's made up it's composed by polyhedra, not by triangles, obviously. So if you have a polyhedral complex that approximates your space, in particular, it means that you're approximating it by something which is locally flat, or at least locally with constant curvature, because you will take this, I mean, you can define this polyhedra only in spaces with constant curvature, like the sphere or Rn or the hyperbolic space, where you can do like barycentric combinations and stuff like that. And this implies constraints, really strong constraints on the curvatures of M. So on the sectional curvature and on the global curvature tensor. So you need some global, not only local, but global inequalities to be satisfied by the curvature, which is usually not the case. I mean, it's a very restrictive condition. So also, this process of approximating a space with triangles, tetrahedron, polyhedron, or simplicial complexes may not work if you do it naively, or if you want to be able to do nice computations of these polyhedra, so if you want them to be taken in some very nice Euclidean space. You have to curve them in some way. You have to remember the metric on M in these triangles, polyhedra, or whatever, which is actually what you don't do when you triangulate something. So when you approximate a curve with a polygonal curve, with a polygonal line, you are using the fact that the polygonal line is composed by segments which are geodesics in Rn. When you triangulate a surface, you are substituting to a piece of the surface a small triangle, which is a flat triangle in the Euclidean space. So you're actually approximating something with pieces of zero curvature in that case. You can allow constant curvature, but if you allow any kind of curvature, then, I mean, they're not simple pieces anymore. They're as complicated as the manifold with regards to the local structure. So if you allow that, you need to do computations differently. Another example are geodesics, and now we think about graphs. So let's say we have a surface in R3 and random points, quite dense. I mean, it's epsilon net or something like that. We can build the associated graph. We can choose between K and N or epsilon neighborhood algorithm, and we can compute distances between faraway points using the Dijkstra algorithm to find the, well, not smallest, shortest path on the graph. However, I mean, this is what isomap does. However, consider something like this. Well, we didn't really meet this guy, the S-shape, but we met the Swiss roll, which is more or less the same thing. This is another standard data set for dimensionality reduction. You notice that here they removed a part from the data set, so we have a hole in it. What happens is that Dijkstra algorithm won't work here. I mean, it will work. It will give you the shortest path on the graph. It works. I mean, it's not that. But it won't be approximating geodesic distances. And why? Well, I mean, consider the parameter space of that object. You have a strip, a rectangle, with some obstacle in here. So this part you cannot go through. And let's say you want to go from here to here. Now, if this hole is closed, so if we cannot travel on the boundary of the rectangle, there is no shortest geodesic. However, you can approximate, I mean, what you would like to do is to do something like this. And then go closer and closer to the border of the rectangle. What's the problem? I mean, this is the minimizing path. What is the problem? Well, the problem is that we cannot move on the manifold. We have to move on the graph. And we don't have any control on how the graph is built. So we'll end up doing something like this, moving a small step, so the problem is that typically you won't be moving in the right direction, not always. And if you are more or less moving in the parameter space straight, then it makes no such difference. But if you have to move around something, then these small deviations do sum up to something. And the length of the green path diverges significantly from the length of the orange one. So that's what happens when you have a hole, when you have non-convexity. And that's why isomap doesn't really work well with non-convex things. And this is, so if you want to study geodesic distances using a graph created by the local behavior and then using just the combinatorial information of the graph, for example, with Dijkstra algorithm, doesn't work. So it works if the space is nice, is very nice, it's convex, maybe also locally flat, which is the best hypothesis. In that case, isomap will give you the really isometric embedding, and then in that case, the Dijkstra algorithm will give you almost the exact length of geodesics, up to an error which is inevitable because you have discretized everything. But if you let epsilon go to 0, you will get the right answer. You won't get it if you have holes. So in particular, if you apply isomap to it's not the subject, the topic here, but if you apply isomap to this thing, you won't recover the what I drew before, but you will get something well, maybe not this long, but something shaped like this with the bigger hole inside. So it will overestimate the dimension of the hole in a sense, because it thinks that the paths going around the wall are longer than they actually are. So this will be the result with isomap. Because the length of the geodesics from one side to the other are overestimated. So for isomap, the hole is bigger than it really is. Now another example is the plus-Beltrami operator. We already saw it. We already stated it. if you have points on your manifold and they are not evenly distributed, the graph Laplacian and the Laplace-Beltrami operator will differ by a term which involves the distribution, the density of your data points. So you take their density with respect to the volume of the manifold, and so the number of points for unit of volume, in a sense. And the graph Laplacian and the Laplace-Beltrami operator, I mean, the graph Laplacian will not tend to the Laplace-Beltrami operator unless the density tends to the uniform density, because there will be a difference between them, which is of the form Laplacian of Q over Q here, and this part amplifies the oscillations of the density. So in practice, you never have uniform density. I mean, if you have random points from a data set or something like that, there is no reason to suppose that they are perfectly uniform on your manifold. I mean, absolutely, unless they are sampled from your manifold. But if they are taken from some real-life experiment or such, they won't have uniform density. So that's why in the discretization of the Laplacian that I showed you some lectures ago, there was also a matrix M, and we were solving an equation which looked like this. And not just, I mean, as opposed to the eigenvalue equation. So that M accounts for the, I said back then, the importance of the points, meaning how many neighbors they have. How dense is the neighborhood? I mean, how many points are there near them with respect to other points? If you remember, this M was a diagonal matrix. On the diagonal, there were the measures of the sets we decomposed the manifold, which were contained inside balls of radius epsilon around every point. So something like that. This M accounts for how separated or near are the points around each other point. So how big or small are these pieces, each one containing one point in which we cut our manifold. So now these are examples of when things do not work well. It doesn't mean that you cannot do it, it means that you cannot do it that way. Now, there are two main structures that are used in approximating a manifold: graphs, neighbors graph, and simplicial complexes. Simplicial complexes are just multigraphs. I mean, graphs with some addition. You don't only have edges, you have more things, faces and volumes and stuff like that. I don't want to enter the precise definition of simplicial complexes. Let's say something like a triangulation, like a, building your manifold with either polyhedra or actually in simplicial complexes they would be tetrahedra, or I mean copies of the standard simplex in Rn. If we use graphs, we have two choices to make. How do we sample vertex points, which was never a choice for us because we were given points until now. So we were interested in when we are given points and we want to understand them, to learn the manifold. But in general, if you are approximating a manifold, you should also decide how to sample points and how to draw edges, how to connect points. So the answer to the second question was I mean, there are a lot of answers you can give, but the most popular ones were the KNN algorithm, so the K nearest neighbors, and the epsilon neighbors algorithm. Why should one be interested also in producing this kind of approximation when we already have the manifold, when we already know the manifold? Well, for example, to test algorithms. I mean, all the data sets we saw, the synthetic ones, the Swiss roll, the S-shape, they were all produced by sampling points on manifolds. And depending on what we want to test, it is important that we know if our sampling allows us to estimate something accurately or not. For simplicial complexes, the main choice is, in fact, how to map the standard simplex into M with given vertices. So, for example, once we have the points we want, so we still have to sample points, to sample vertices. It is the same as in graphs. But then the main difference is how to place the triangles. So, in what sense these triangles correspond to the manifold? Now, there are a number of ways. I will be explaining two of them really quickly. I mean, quickly. Not too many details. The first one is the Karcher simplex. So let S be the standard N simplex. So, for example, in R3, you consider the three unit vectors. So this is E1, E2, and E3. And the standard simplex, the standard 2 simplex, the triangle, this is S inside R3. So all the points in S are written as a sum lambda I EI with lambda 1 plus lambda 2 plus lambda 3 equal 1, and all of them greater or equal than 0. So it's the convex combination of E1, E2, E3. Or I should write E0, E1, E2 because I will be writing them that way later. But anyway, damage is done. So the standard simplex is the convex combination of the basis vectors of Rn plus 1. If you do it in R3, you get a triangle. If you do it in R4, you get a tetrahedron with vertices on the... Okay, so when we will be considering a point inside the simplex, we will just be considering its coordinates, because the basis is the standard basis, the canonical basis of Rn. Now we consider points in M. So we have the vertices of our wannabe simplex. So P0, Pn in M, and we take 1 point lambda in the simplex S. So we define the map E lambda from M to R that for every point of M computes the distance squared from that point to each vertex and multiplies it by the corresponding lambda I. So as I told you before, here the coordinates go from 0 to n. Sorry for that. So this is lambda 0, the distance squared from A to P0, lambda 1, distance squared from A to P1, etc. The sum of all these terms. Now, if M is nice enough, there is a radius such that if we take all the points inside a ball of that radius, then on that ball, this function has a global minimum. Only one, a unique global minimum. you can write this in terms of the zero of the gradient. You can compute everything. I mean, it's not difficult. M nice enough means, okay, M nice enough. There are three kinds of conditions. Curvature bounds. So usually either sectional curvature bounds or Ricci curvature bounds. So there shouldn't be directions where M bends too sharply. Then exp should be exp p, let's say, should be uniformly nice in P. So for example, well, the main thing would be the injectivity radius, which I haven't talked about, but the point is that xp is nice, because if you fix P, xp is a diffeomorphism between a neighborhood of 0 in the tangent space and the neighborhood of P in M. Now, how big are these neighborhoods varies with P. Now we want some uniform estimate on how big these neighborhoods are for P varying in M. And the third kind of condition is convexity in some sense. In some sense, meaning that you can have analytical requests like the, I mean, also in R, when you say that a function is convex, you think about two things. The geometric property, if you join 2 points on the graph, the segment should be all on one side of the graph, and the analytic property that the second derivative should be positive. On a manifold, you have 2 kinds of conditions: some positivity on, well, curvatures, which correspond more or less to second derivatives in a way, and geometric conditions, which will be about geodesics. But anyway, I don't want to enter in this kind of technicalities. There are some conditions which usually you can if you are in a compact space, usually almost everything is true, or at least easy to check. Then under these kind of conditions, we can cover M in balls with fixed radius, and on each ball, E lambda has a global minimum if all the points we use, all the P0, Pn, the vertices we use, are inside VR. Now, if you try and solve this optimization problem in Rn with some n+1 points, the minimum will be the point with coordinates lambda 0, lambda n. So in Rn, the solution of to the minimization of this function is the point given by lambda. I mean, with coordinates lambda 0, lambda n with respect to P0, Pn. So will be the point lambda 0, P0 plus lambda 1, P1 plus lambda 2, P2 plus lambda n, Pn. Sorry. So it will be the convex combination of P0, Pn with coefficients lambda 0, lambda n. This will be the minimum. So this result, in a sense, allows us to associate to every lambda a convex combination, which is called the Karcher mean, of P0, Pn with coefficients lambda 0, lambda n. we define x from S to M by sending lambda to the global minimum in BR. So we fix P0, Pn. The image of all the simplex is called Karcher simplex, and it's a set with vertices, in some sense, P0, Pn. Now, this map has a lot of nice properties, but we don't know much about it. So it's difficult to compute, and in general, it's hard to prove that it's injective or it's well behaved with respect to geodesics. I mean, it presents a lot of problems. However, it offers good approximations for curvature, for functions, so you can define functions and you can approximate them quite easily if you know them only on a dense set of points. And you can test conditions on this lambda. So for each point, you can express it as a combination of some vertices, and all the requirements you have on the density, epsilon nets, whatever, close enough, not close, not too close, not too dense, etc. You can transfer them on the parameter lambda. So you have problems in Rn plus 1. And you can do all the computations. The problem, the issue here is to carry this construction on for your general manifold. Now, another thing you can do is the following. You build around each point a local triangulation. So it will be a simplicial decomposition, actually. But in this case, it's usually called triangulation. I don't know why. You triangulate the tangent space, so a fine triangulation. So you decompose a neighborhood of the origin of your tangent space in a simplicial way, so in union of simplexes. And then you send everything on M via the exponential map. Now, you will need more or less the same conditions as before. So we will need bounds on curvature, a good behavior, a global good behavior of the exponential map around every point, and some convexity properties. Because if you use an affine triangulation of the tangent, it means that you're using lines through the origin as a first step, and these go to geodesics. So you want some good behavior of geodesics. If you put the right conditions on the affine triangulation, so you have a couple of conditions that you have to put on the affine triangulation, a sort of compatibility conditions, then you can do it around, locally around some points, and you can glue the results up. So you will have a simplicial complex around each point of M, around the number of points. If you do it carefully with some conditions, with some attention, you can join these local triangulations in a controlled way. So meaning that you don't have to decompose. Usually when you join two triangulations, it may happen that sides do not, for example, you have two triangles and sides do not match exactly, so there is something like that. So something happens, you do everything around this point. You do everything around this point, so you are triangulating your manifold with some things like this. So nothing tells you that when you do the same, when you do the corresponding process here, that you will end up with something that glues up correctly. So what happens is that you usually refine your triangulation. So you split your simplexes in smaller pieces until they fit together. Now, locally, the number of splittings is finite because, it's intersection between polyhedra, so it's a polyhedron again. So you can divide it. Sorry for a second. So you can locally divide it in a finite number of pieces. However, when you do it all over your manifold, well, it may happen that the supremum of this number is not finite anymore, or it's really big, or, I mean, something which was bounded before is not bounded by the same constants anymore, and you cannot have a nice control on this bound. So if you just do random triangulations, it won't work. However, if you construct the local triangulations with some good properties, you have good hopes to join them together in a nice way. The requirements are quite technical, obviously, because they involve estimated quantities related to triangulation, but in the end, it's possible to do it. So you have something which is global, control the parameters of the triangulation, so the number of pieces, the areas, volumes, length of the faces are within some bounds, and they're locally given by geodesics. Now, this is especially useful when you estimate Laplace-Beltrami eigenvalues. There is a way of defining a Laplace-Beltrami operator on the triangulation, which is obviously a combinatorial thing, and this will converge nicely to the Laplace-Beltrami eigenvalues on the manifold. So these are two examples of ways of obtaining triangulation, simplicial complexes on your manifold, which are quite different. But anyway, in any case, both in graphs and in simplicial complexes, everything starts by selecting points. So we need to select points on our manifold. So we want to sample points on the manifold. Now, obvious fact, a uniform sampling on the parameter space of a parameterization does not give you usually a uniform distribution of points on your manifold. Just take your favorite word map, flat on a page, and sample a grid of points, a lattice of points with a given side, and then transfer it to the globe. It's not uniform. I mean, in any case, in no case it will be uniform, because this could be a proof that the Earth isn't flat, but anyway, at least in the curvature sense. Also, I mean, maybe you don't really need uniform distribution on your manifold, but maybe you need something less strong. For example, you need the distances obey some sort of uniform distribution, or the minimum distance of a point from the rest of the points obeys some uniform distribution. Everything is false. I mean, everything depends on the curvature, and so everything is false because your parameter space is Rn, which is flat, and you are wrapping it up on a manifold which is not flat anymore. Now, on the other hand, sampling on the manifold is, well, impossible in some situations because the manifold is an abstract manifold, you don't have any models of it, or impractical because the manifold is embedded in some Rn, but then it means that you should sample how? In Rn, trying to sample only on the manifold. I mean, it's very complicated to efficiently implement something like that. I mean, in principle, it's possible. I mean, just something with the density, which is the volume measure of your manifold, but in practice it's quite hard to get the actual points. So the common solution for this, I mean, it's not a solution, the common idea for a solution is to sample from the parameter space, but with respect not to the Lebesgue measure, but to the volume measure induced by the pullback metric. So every time, so let's say you have here a parameter space. And here you have some Rn where you have some submanifold, and you have your parameterization map. Which, I don't know, sends things to... So, for example, these lines are sent to these circles and so on. Okay. Now, usually, you can decompose this map into two steps. I mean, it's just... on one side it's obvious, on the other one it's very useful. So at first you wrap up your parameter space into the abstract manifold. And then you send it to Rn in a volume-preserving way. Now, if you remember, the volume was given by the square root of the determinant of the metric. So you just need the metric on the determinant of the metric on here, but this determinant of the metric is in fact the determinant. I mean, if you work things out here, this becomes the determinant of the Jacobian matrix of phi. So it's what you already know from not that phi. Haha. See, it's what you already know in Rn, in R3 when you compute the area of a surface. If you write it down, it's exactly this kind of procedure. So the volume measure induced by the pullback metric is just the determinant of the Jacobian of the parameterization of the abstract manifold. So it's the right combination of minors of the matrix that gives you the parameterization in Rn. Now, a pair of practical things on here. The first one is how to sample points. So the usual strategy is the rejection algorithm. You sample a lot of points with a uniform distribution on your parameter space, who cares? Really a lot more than you need. And then you accept or reject them according to the distribution given by the Jacobian determinant. Obviously, no one, I mean, this will obviously represent the right distribution. The point is how many samples you get in the end, you don't know. So you have to repeat the algorithm, sampling from the uniform distribution, and then accepting or rejecting points depending on the the Jacobian determinant, over and over again until you reach the right number of samples. So this is what usually is done. It's a very consolidated algorithm, which is called the rejection algorithm. You can find it in every package, module, whatever, which has to do with sampling. And now another final notice that apart from particular situations, sampling locally, so you have a ball, you have the volume of a ball in your manifold, and you sample locally from that distribution, and then gluing the results does not coincide with sampling globally. So they are two different processes. You can see it, not easily, but I mean it's just technicalities, by writing down the associated Markov processes and noticing that they're different. Also in the finite case. So they will end up having different behaviors, and they will give different samples of points. Samples with different distributions of points. And I will stop here.